Okay, so our question asks, what is the force F on the negative 10 nanocoulomb charge? Express your answer as a magnitude and an angle measure clockwise or counterclockwise from the x-axis. The first thing we should do is label the charges so we can identify them later in the problem. So this will be charge 1, this will be charge 2, and this will be charge 3. Okay, and the next thing we should do is find the forces of charge 2 on 1 and charge 3 on 1 separately using Coulomb's law. And just a reminder, Coulomb's law is equal to K times Q1 times Q2 over R squared times R hat. Q1 and Q2 being the charges, K being a constant, and R being the distance. Okay, let's start with the charge F2 on 1. First we have our K, which is equal to 9 times 10 to the 9th, times Q1, which over here is negative 10 nanocoulombs, and charge 2, which is negative 5 nanocoulombs, divided by our distance squared, which is in centimeters, and it should be in meters, so we're going to change that to 1 times 10 to the negative 2 meters squared. Now you should always put absolute values around the charges. When you calculate all that out, you should get F2 on 1 equals 4.5 times 10 to the negative 3rd newtons. Next we'll do the force of 3 on 1. In order to do this, we have to find the distance between charge 3 on charge 1, which requires a little bit of trig. So we have our diagram here. This is charge 1, and this is charge 2. And we have this as 1 centimeter, and this is 3 centimeters. So if you draw a little line here, you can identify that as the hypotenuse, so you can just use the Pythagorean theorem to find the value of the hypotenuse, which we'll label R. And if you do that math correctly, you should get 3.16 centimeters as your hypotenuse. And then we'll plug that in to Coulomb's law. So again, we use K constant times charge of 1 times the charge of 3 this time, all divided by our distance, which we just calculated. Again, has to be in meters, so we're going to say 3.16 times 10 to the negative 2 squared. And if you do all those calculations correctly, the force of 3 on 1 should be 1.35 times 10 to the negative 3rd newtons. Next, we need to find the x and y components of the forces F2 and F2 on 1 and F3 on 1. Now because 2 and 1 are both negative, 2 will push 1 away in the negative direction. Something like this. Now for the force F2 on 1 in the x component, there actually is no x component because it goes straight down, so the x component of the force 2 on 1 is going to be 0. The y, on the other hand, will be what we had previously calculated to be 4.5 times 10 to the negative 3rd newtons. But as we established, the second charge is pushing the first charge in the negative direction, so the force of F2 in the y component will be negative. The force 3 and 1 are opposite signs, so the force of 3 is actually going to pull charge 1 up and to the left, like this. We can use this vector to help us find the components by drawing a right triangle. And as we had established previously, this value down here will be 3 centimeters, and this will be 1 centimeter. And this angle we'll call theta. To find theta, we're going to use some trigonometry again. We're going to use the inverse tangent function, and we're going to set it equal to opposite over adjacent, which is going to be 1 over 3, which should give us a theta value of 18.43 degrees. To find the force of 3 on 1 in the x direction, again we're going to use some trig. We're going to take the force, which we previously computed to be this, and multiply it by cosine of the angle that we previously computed. And if you do that right, you should get 1.28 times 10 to the negative third newtons. Now, since it's pulling it to the left in the x component, our x component will be negative. For the y component, we're going to do something similar. We'll take the force and multiply it this time by sine of the angle to get 0.427 times 10 to the negative third newtons. Next, we're going to find the net x component and the net y component forces. So to find the net x, we're going to take the force of 2(1) on the x and add it to the force of 3(1) on the x, which should give you 0 minus 1.28 times 10 to the negative third. So your F net in the x component should be negative 1.28 times 10 to the negative third newtons. For the F net in the y direction, we're going to add F21y plus F31y, which will have negative 4.5 times 10 to the negative third newtons plus 0.427 times 10 to the negative third newtons. This will give us a value of negative 4.07 times 10 to the negative third newtons. Next, we're going to use the net forces that we just calculated to calculate the magnitude and the angle. So the force is going to equal the square root of F net x squared plus F net y squared. And if you plug that in, it will look like this, negative 1.28 times 10 to the negative third squared plus negative 4.07 times 10 to the negative third squared. Ultimately, this will give us a magnitude of 4.3 times 10 to the negative third. To calculate the angle, we're going to take the inverse tangent of f net y divided by f net x, which is going to be negative 4.07 times 10 to the negative third divided by negative 1.28 times 10 to the negative third, which will equal 72.5 degrees. Finally, we're going to draw out our x and y vectors to find out where this angle is oriented. So we'll start with an x and a y axis. And then the x, because the x and the y components are both negative, as we previously calculated, we know that the x is going to be from here to here somewhere, and the y will then be from here to here somewhere, meaning the angle has to come down from here.